All right. Well, what we have right here is we're going to do a quick tutorial on how to find absolute extremum. All right, and we have a function. This is number 4. This is an even one. You can check out the odd ones in there. But in order to find absolute extremum, we're going to use or apply with the extreme value theorem. Now, in the extreme value theorem, there are some conditions that have to be met first. In order for the extreme value to work, the function that you're using, so in this case f of x needs to be continuous. It needs to be also closed, all right, on an interval from a to b. Now, on this, we can see that on this interval, this function is continuous, and it also is a closed interval. So yes, the extreme value would work on here. Now, to figure out where these extreme values are, now these are talking about the absolute max and mins. All right, so absolute max and mins. We are looking in 2 different locations. Absolute extremum occur at endpoints of a function on a closed interval, and also occur in interior points. Wow. To test these endpoints, what we're going to do is we're going to substitute in these values into the function. So we're going to first test the endpoints, and we're going to test out, in this case, f of 0. So we plug in 0, and we have 0 over 1, and that's going to equal 0. So we have a value of 0, 0. We test out our second point, our second endpoint, which is f of 2. And we have 2 over, appears the square root of 5, which is going to be equal to 2 square root of 5 over 5, and that's our other endpoint. The next part is we're going to test our interior points. Now, to test the interior points are where we have critical numbers. Okay, so when we have critical numbers, those are possible locations of absolute extremum. All right, and the critical numbers, if you recall, are when f prime equals 0 and when f prime does not exist. So at these different values, we're going to test this function. So we're going to find out where f prime equals 0. So right here, I'm going to use green here. Separate this. F prime equals 0. Well, first find f prime. So I'm going to use the quotient rule. I'll take this function right here. Find f prime, so I have derivative of x to the top, which is 1. We use the quotient. Again. Take the derivative, or times the bottom, which is x squared plus 1. Minus the derivative of the bottom, which is going to be 1/2, times the quantity x squared plus 1. It's going to turn to the negative 1/2 power. Times the inside, which is 2x. Times the top, which is x. Now, all of this, of course, is going to be over x squared, so we're going to have the quantity x squared plus 1. And we square that denominator right here. I'm going to move on. And now we want to figure out where does this equal 0. So graph it down, push that down a little bit. We have this equal to 0, or, well, we can first see that, first off, when this equals 0, we need to figure out when the numerator equals 0. So we got to simplify this function. To do that, I'm going to just rewrite some things. The numerator, and we can see that this 2 and this 2 cancel out. And then we'll have minus, it appears, x squared, and then we have the square root of x squared plus 1 right there. We can take the denominator right here, and we can make that 1 over x squared plus 1. Simplify that a little bit. All right? From here, we're going to multiply top and bottom by square root of x squared, get a common denominator, square root of x squared plus 1. And what we have is x squared plus 1 minus x squared all over the square root of x squared plus 1 times that quantity 1 over x squared plus 1. From here, we identify that the numerator, when we find the zeros, this will cancel out and we're left with 1. So f prime, all right, does that ever equal 1? Well, it appears that this will never equal 0. So f prime will never equal 0. So there is no of this one. So this one doesn't exist. Now we find out if f prime ever does not exist. Well, we look at the denominator, and we realize that this value will never equal 0 as well. So are there any critical numbers where we can test? The answer is no. No critical numbers. All right. Well, that's a quandary, because in order to find extreme values, we know that either they're in the endpoints or interior points. So it appears from our analysis that we are only comparing the endpoints this time. So here, excuse me, our endpoints find that we have an absolute min appears to be at 0, 0. And then we have an absolute max here at 2, and then 2 squared root of 5 over 5. Well, if you put this in your calculator, this function, I'll put it up there again. All right, let's verify this using our grapher, because that's what this problem asks us also to do. Let's put this into our graphing calculator, and I did that. And on the bottom, let's identify if this is accurate. Well, looking at this graph, we are starting at 0, and we're going to 2. And what we have right here is this is the interval we are looking at. Well, obviously, looking at this interval, we can see that there are no critical points, all right, because there is no value where f prime does not equal 0, and obviously f prime does not, there's nowhere where it does not exist on this interval. So we have no critical numbers, but so that means we just look at our endpoints. Our endpoint here, obviously at 0, 0, yes, this is our min, and we can identify this point over here at 2 appears to be whatever that is. What we found out it was going to be 2 squared root of 5 over 5. And that is our absolute max. So we once again verified using a graph what we found through our analysis. In conclusion, to recap, in order to use the absolute extreme value theorem, or to find the absolute extreme values, you check the endpoints and the interior points. That's the key. Endpoints, you plug in the values in, and the interior points, you have to find the critical numbers, and then all right, identify what those values are. All right, so good luck on finding absolute min maxes.